All right, students, welcome to the Neon Lights and Other Discharge Lamps simulation, which is offered here through the University of Colorado. We've adapted it for an activity that we're going to call the Bright Line Simulation. And I'm going to show you how to use this little object to simulate collecting data on real electrons and real atoms and how they respond to being excited. According to the Bohr model, the energy levels which are possible for a given atom are like stairs on a staircase. You're either on stair 1 or stair 2. You're never in between. So you're either at the ground state, energy 1, here showed as 1 on this atom, or you're at 2, or perhaps 3, etc. It's going to be, rather than continuously changing, it's going to be discrete. It's either 1 or 2, 2 or 3, that sort of thing. See this one time, I'm going to set the power up. And we are going to fire a single electron at this atom, which right now has an electron in the ground state of 1. So we're going to hit it with an electron. And when we do, it momentarily went up to ground state 4 before settling back down to 1. Now, it picks up energy. It causes the electron to go up to a higher level, but that's not stable, so it immediately returns to the ground state. But as it does, it releases the difference in the two energy levels as a photon, which has a particular color. Let's do it again. Let's see if we go to 4 again. Well, this time we went to 3, and then to 2, we saw a different color photon emitted as a consequence. Do it again. Again, that was 2, a purple photon. We'll do it again. That was 3 and 4. We got 3 different colors out. And so on and so forth. And if we do that, we do it that way, we can keep track of each one at a single time. It's not terribly efficient. So let's now make it go continuously, and let's adjust the stream to 100%. So we're sending a constant stream. We're constantly exciting this atom and causing electrons to pop up and down, as you see over here, the different energy levels. And as they do, they release different colored photons, some blue, some purple. Every now and then we might see a red, like we see one there. Some are more common than others. Now, what exactly are we simulating? What is the source of this radiation that we're trying to keep track of? Well, the source in a proper scientific lab is what's called a discharge lamp. So I have a picture here, and you can see here that we actually have tubes. This is hydrogen in pink, mercury kind of a light blue, sodium vapor, a yellow-orangish color, and neon, the brilliant red of neon. These are tubes that are just filled with different elements in the gaseous state. They're hot, and they get them to the gaseous state, and they get them sufficiently energetic, they glow. And the color we're seeing is the color of the photons that are emitted by the various gases. And you'll notice that since hydrogen, and energized hydrogen is basically just a single proton, you get that hot pink color. As I've told you, protons, actually, you get them hot enough, they glow a kind of reddish pink color, and there it is. You're actually seeing it there in that picture. So we've been running this for a while, and we can see different colors being produced. There'll be one dominant color, of course, that was why the gas tube will have a particular color, but there's different colored photons being released, and some are being released more than others. So to keep track of that, we're going to now we're going to go here, we're going to click this, we're going to engage the spectrometer. And what you're going to see is you're going to start seeing individual lines of color being produced according to how often that particular color of photon is released. And so you can probably see that there's a line there, there's a line there, there's a line there, and there's a scale at the bottom. The scale is in nanometers. And you know, this is still time consuming. You'll notice that we're getting things over here. This is the far ultraviolet. These are waves that are too small for our eyeballs to detect. And over here, we've got the far infrared. There's photons over here, and these are waves that are too big for our eyeballs to detect. No, our eyeballs are only tuned for this narrow range in the middle. And at this point, we now see that we have 1, 2, 3, 4 different lines of color forming. The most common, of course, is purple. You see that that's happening the most. The next is a deep blue, and the red, which is that's not occurring nearly as often. Anyway, this is data that we can collect, we can measure, we can estimate about where the wavelength is in terms of its size. Like this is close to 400, whereas this one is close to 500, and this one is somewhere between 600 and 700. We can guess that, and we can observe the colors. So that's the basic how you would go about doing the actual data. Now, if you want to go faster, we can put multiple atoms into the picture. And again, we can have a steady stream. We can put it at 100%. And we can mess with the voltage, so there's a lot of it. And we can display the spectrometer. And you can get data somewhat faster this way. So that's how you're going to use this simulation. You'll do it for hydrogen, and you'll get one pattern of lines, and you'll do it for mercury, and you'll get a different pattern of lines, different colors. Do it for sodium, different pattern of lines, different colors. Do it for neon, different pattern of lines and different colors. I know I sound like a broken record there, but the key thing here is that every element has its own unique signature. We see a unique pattern of lines. Some have more lines than others, and none of them have the same 2 or 3 or 4 combinations of colored lines. Every one of these spectrum is unique for that element. It functions like a fingerprint that absolutely identifies that element. And so we can take really any source of light that's bouncing off of atoms, and we can tell you what elements are present in the source of the original light. Even if that light comes from a distant star, millions of light years away, we can still look and say what elements are present in the surface of that star, which is pretty remarkable. Okay, so you're going to get data of this nature, and the key thing is that you need to be able to display the data inside the actual lab. So now I'm going to go and open the actual lab for you to see, so you can see what that looks like. All right, so this is the handout for how we're going to use the bright line simulation that I just showed you. The actual address online is given right here, so you can just select it and Control-C, copy it, and cut and paste it into a search engine in order to get to the simulation. Some basic instructions are here, and they agree with what I previously showed you. Now, below that, we have a little guide, and the guides suggest that we have a spectrum. You see the colors. Underneath it, there is a scale, and the scale is just like the scale that appears in the simulation. It is given in nanometers, and nanometers are, 1 billionth of a meter. They're very small, 10 to the negative 9th meters, okay? So it's probably going to be necessary for you to take whatever numbers are given and multiply them by 10 to the negative 9th. Why? To convert them into meters. Because once we convert them into meters, we'll be able to figure out, how big the wave is, how often it comes, and from that, we can figure out the actual amount of energy associated with that. But before we get to the math, let's just talk about how we would plot the data. Let's say that we're doing hydrogen, and let's say that the first thing we observe is a wave right at 500. Okay, so to show that wave, we need to put a line right on the 500 for the spectral line of hydrogen. Okay, so for that, we're going to insert. I'm going to click on this button that says Insert right here at the top. Next to it, we're going to click on Shapes. Inside Shapes, we're going to choose the second thing, which is labeled Line. Having chosen that, I can now make a line. I'm going to try to make a line that's straight up and down, like right on the 500. Okay, I'm going to try to make it fit. I'm going to try to make it the right distance. So I might have to fiddle with it a little bit. I'll click on it again. And when you see the little circles, that allows you to adjust the length of the line, which I'm doing. And I'm also trying to keep it straight. So the first time you draw the line, it's going to be a little bit, it's a little bit aggravating to try to get it just the right length. A little time consuming. However, once you get it set up that way, you're going to click on it. And once you've got in position, you're going to right click and that will get you an option that says Format Shape. Okay, so now we'll come over here to the Format Shape box. And, just to make things clear, I'm going to move myself out of the way so we can see what we're looking at right here. Okay, so in the Format Shape, so in the Format Shape, there's places where you can mess with your line. So first of all, I'd like to get my line to be bigger. It's very thin here. So I'm going to go here where it says width, and I'm going to push the up arrow until my line is nice and thick and easy to see. Now I'm going to say, well, if I saw a line at 500, it's not going to be this dark blue color. It's going to be like a blue-green color, according to the spectrum guide here. So I'll go inside here. I'll go inside here where it says color, and I will click, and I'm going to try to choose a color that matches that, a kind of blue-greenish color. Be nice if I wasn't in the way, so I'll do that. Move that around. Okay, I need kind of a blue-greenish color, about like that. So I go that, click OK, and now I've got that color there. All right, let's say that I also wanted to have a line on the 600. The 600 looks like an orange. Well, I don't have to do everything from scratch. I can select my previous line, and I can click Control-C. I'm going to make a copy of that line. Then I'm going to go Control-V. V as in Victor. And a copy of that line with that color will appear. Well, I'm going to put this line right on the 600. According to my key, that should be an orangish color. So I'll come over here to Format Shape, and I will find a red-orange that matches what I expect. Too orangey, maybe a little bit more red. There we go. And let's say I want to do a 700 too. Okay. All right. Well, all right. So again, grab my line. Control-V to paste it after copying it. Position it over where I think it needs to go. I'm going to go 700, and I'm going to make this a brilliant red, even a dark red, like so. Okay, so that's precisely how you'll do it. Again, you'll create the line by inserting the shape. You'll choose line, and you'll plot it in, you'll draw it, and then you'll right-click it so that you can edit the shape and make the line thicker, easy to see, and adjust the color. And after that, you never have to make a line from scratch again. You just cut and paste and adjust its position on and color. Now, let's talk about what, oops, didn't want to do that. Let's talk about what we're going to do for the rest. This is pretty straightforward. On the second page, there's math. And the math requires us to determine the frequency and also the energy. We're not going to do it for all four elements. We are going to do hydrogen and sodium. And hydrogen will have 4 lines, and sodium will have 2 lines. And so we're going to have to calculate 6 different colors. We're actually going to convert the colors into frequencies. The way we're going to do that is we're going to take whatever number, the size of the wave is the wavelength, and you're going to take that, whatever number you chose, and you're going to multiply it by this number, 10 to the negative 9th. And so you'll end up with a very tiny, small number in meters, and then you will apply this formula. The formula says that the speed of light is a constant that's almost always 3 times 10 to the 8th meters per second. So the product of the wavelength lambda and the frequency f is always going to be that number, the speed of light, which is a constant in a vacuum. And since the speed of light is a constant, and since it always equals the product of the wavelength and the frequency, that means the speed of light divided by the wavelength gives you the frequency, and the speed of light divided by the frequency gives you the wavelength. You can use those simple relationships to calculate the frequency of each of those 6 colors. Now, once you have that frequency, this becomes really simple. Whatever that number is, you're going to whatever the number for the frequency is, you're going to multiply it by Planck's constant. Now, Planck's constant is a hard number to put into a calculator, but once you put it into the calculator, it's just multiplication. So you'll do that, and the product of this number, Planck's constant, and the frequency will be the actual amount of energy associated with the photon of a particular color. And you'll be able to see that different colors have different energies. And you might even be able to notice that if you think about it, if you notice it, you may figure out, gee, these may be related to one another in a whole number ratio. But we won't do that math. I'm just saying the slicker student may recognize that on its own. Okay, so that's the gist of it. I've showed you the simulation. I've shown you how you're going to put it on here, and then I've drawn your attention to the math that will be used to do this. Don't worry, I will also present the math in class. I will do actual examples and problems both in class and in student support to show you how to do it. But it all starts with you going online to this particular site, using the Brightline simulation to collect the actual data, the actual frequencies and colors for each of 4 elements. You got to do that first before we do anything else. Okay, this is really a fascinating activity, and I look forward to seeing your work. And take care until we meet again. Bye-bye.